Hello, geometry. Welcome to the final lesson of topic 11 on 2 and 3 dimensional models, 11.4 on spheres. So again, let's just talk about what a sphere is, right? So a sphere is your three-dimensional circle. So typically you draw a circle and then you have like a oval shaped 3D ring that's supposed to represent the depth of this ball, this sphere. And again, it still has a radius and diameter. So we're mainly focused on the radius from the center of the sphere out to the outside surface of the sphere. Okay. All right, so the first thing I'm going to do here is I want to develop the formula for the volume of a sphere. And to do this, we're going to use Cavalier's principle. If you remember, Cavalier's principle says that any two solids that have the same cross-sectional area everywhere and the same height will have the same volume. So we're going to use that principle here. So in this picture here, I have a hemisphere. This hemisphere is going to have a radius of r. So this radius will be r, and it has a height of r, right? Because it's half of the hemisphere, and again, if we go straight up, that's also r. Over here, this cylinder, okay, is going to have a radius of r again, and it has a height of r. Okay. Now, what we're going to do here is we're going to intersect this cylinder with a cone. All right, so we're going to do it just like this. So I'm going to draw in this cone. And what's going to happen here is this cone is going to then create a cross-sectional circle because a cone has a circular base. And what we're going to say here is that the area right here of this circular cross-section is going to equal the area of what I call this washer, right, which is the outside circle subtracting the inside circle. They both have the same height, right? This r, and again, we're going to talk about what the height is here as well. But we're going to show that these two cross sections are equal in area, right? So here's what we're going to do. We're going up a height, say h. So this height is h on both sides. Okay. So over here, what we're going to use is Pythagorean theorem. So for this sphere, I know that this height is h. I know that this is a radius r. We're going to find the radius of this cross-sectional circle, call it x, using Pythagorean theorem. Okay? So a squared plus b squared equals c squared. I don't have a lot of room, so it's going to be squished. The radius is c. Now, again, this is just going to be in terms of x, h, and r, right? This is c. So we're going to do, I'll do x squared plus h squared equals r squared. And I'm just going to subtract h squared on both sides. X squared equals r squared minus h squared. And I'll take the square root to get the value of x, right? And x is equal to the square root of r squared minus h squared. Again, it's not distributive. This is not r minus h. So then the area, this red area, it is a circle, will be area equals pi r squared, right? And our radius is going to be this x, pi times the square root of r squared minus h squared squared, which is going to simplify to pi times r squared minus h squared. I'm going to do it right up here. So the area here equals pi times, and again, this squared and square root cancel. I'm going to leave the r squared minus h squared in parentheses. You could distribute the pi to both, but I'll just do this. So this is the cross-sectional area of the hemisphere right there. Okay, now I'm going to change colors to purple. Let's take a look at this over here. So again, I have raised my height h. So this is going to be a height of h. Okay, the outside cylinder has a radius of r. This inside radius right here, maybe I'll use pink maybe, this inside radius, is going to be also h. Because of the way this cone is shaped and the way that it creates itself, it's going to be an isosceles triangle right here, with this being h and that also being h. Okay? So to find the area of this washer, right, we're going to take the area of the outer circle minus the area of the inner circle. So the area is going to be area of the outer circle. Again, it's a circle, pi, and the radius is r squared. And then the area of the inner circle is going to be pi times h squared. Well, if you factor out that pi r squared minus h squared. These two 3D figures have the same cross-sectional areas. They have the same heights. So because of this, because they have the same areas of the cross-section, same heights, they should have the same volume. All right, well, let's continue on. Okay, so here's that picture again. So again, they both have the same height, r. Okay, so to find the volume of the sphere, we're going to take the volume of the cylinder and subtract the volume of the cone, because that's exactly what we're doing. We're taking this cone and taking it out of the cylinder. All right, so the volume of a cylinder would be pi r squared h, pi. Again, the radiuses are both r, radius, pi r squared. And then the height of this cylinder is also r. Same height over there. Minus, to find the volume of the cone, we'll do 1/3 area of the base, pi r squared, times the height again, and that height is going to be r. And now we're just going to simplify this, right? So this equals pi r cubed minus 1/3 pi r cubed. We're going to make this so it can combine 3/3. So this becomes 2/3 pi r cubed. But now again, I should not have put volume of a sphere here. This is the volume of a hemisphere. So to find the volume of the sphere, we need to double this. So to find the volume of the sphere, we're going to take 2 times 2/3 pi r cubed. And that would be 2 times 2, which is 4/3 pi r cubed. And there's your volume formula. And that is how you find the volume of a sphere. So this was a long, kind of drawn out explanation of why the volume formula is the way it is. Here is your slide that actually presents the volume of a sphere. Again, it's on the OST reference sheet, so you do not have to remember it. And again, I just want to point out that that is a cubed with the r. So because we're doing volume, it is a cubed radius, right? And again, think of volume as 3D. So that is cubed. Okay, so I'm going to stop there. That was a lot to take in, and we'll do 1, 2, 3 problems on the next video.